So this is the video for the group project 2 for the chemical processes problem. And for this problem we have one MATLAB script as well as two MATLAB functions. And the problem is given here. The problem is all about ammonia production, and it's divided into 4 different tasks. So applying mass balances, graphically analyzing the system, optimizing the system, as well as finding the utility cost of the system. So this is the system right here, given this by this flow chart. And we start off fresh feed. We start off composed of nitrogen, hydrogen, inert gas. So that, as well as the recycle feed, is sent to the single pass conversion reactor, which is then sent to the cooler, which is just cooled, which is then sent to the condenser, which is where it gets interesting, because the condenser is where the ammonia will be separated from the rest of the mixture, because the ammonia gets liquefied, and so that gets sent off down here. The rest of the mixture, half of it gets purged and half of it gets sent to the recycle stream, which then meets back up with the fresh feed stream and then starts the process all over again. So for task 1, it asks us here, create a user-defined function which takes these 3 inputs: XIO, which is the mole fraction of inert gas, FSP, the fractional conversion of the reactor, and YP, the fraction of gas leaving the condenser. And it wants us to find these 3 outputs, the variables: NR, which is the moles fed to the reactor, NP, the moles of ammonia produced, as well as FOV, the overall fractional conversion of nitrogen. So this is our main script here. This is our first function. This first function is chemical converter. This is for tasks 1 through 3. This cooling function is for task 4 only. So we start off here, task 1. So this is the user input section for the moles of inert gas, the fraction of fractional conversion of the reactor, FSP, and the fraction of gas leaving the condenser, YP, as well as some data validation. So XIO, input the desired mole fraction of inert gas in the fresh feed. YP, input the desired fraction of gas leaving the condenser, as well as FSP, input desired fractional conversion of the reactor. And these 3 errors, just data validation to make sure the user doesn't mess up and input any wrong numbers. And so here we call to the chemical converter function for our 3 outputs after the user has input their 3 variables. And so these are the 3 outputs we're looking for. So NR, total moles fed to the reactor, NP, moles of ammonia produced, and FOV, overall fractional conversion of nitrogen. And so basically, yeah, we just want to input these 3 variables into chemical converter function, and get the output, these 3 outputs, these 3 variables, moles fed to the reactor, moles of ammonia produced, and the overall fractional conversion. So that's task 1. Task 2 ties into task 1, and task 2 asks us to graphically analyze the system. So basically, task 2 asks us to create 3 separate plots to show the relationship between 3 different graphs, basically. So the first one, NP versus YP, moles of ammonia produced versus the fraction of gas leaving the condenser. The second asks us to plot NP versus FSP, so moles of ammonia produced versus the fractional conversion of the reactor. And figure 3, NP versus XIO, so moles of ammonia produced versus fractional mole fraction of inert gas. And so basically it wants us to graph these three relationships in task 2 after task 1 and analyze it. So yeah, we'll run that and show you how we analyzed it. And then task 3 is basically optimizing the system. So the first 3 tasks are all really tied in together, and it basically asks us to, based on our observations, what of the independent variables, which would we minimize and which would we maximize to optimize the production of ammonia. So given here, what recommendations would you give in order to optimize production of ammonia? So these 3 independent variables: mole fraction of inert gas, fractional conversion of reactor, as well as the fraction of gas leaving the condenser. Basically, what would you maximize and what would you minimize? So we'll run, I'll show you the function first, chemical converter. Basically we split our feeds and our streams. So we start off fresh feed, and we have our reactor feed, which is recycle and fresh feed, and R, which is moles fed to the reactor, which is one of the 3 outputs we're looking for in task 1. Moles leaving the reactor, moles of ammonia produced, NP, which is another output that we're looking for in task 1. Leaving the condenser, purge, recycle feed, as well as fractional overall nitrogen conversion. So that's our 3rd and final output that we're looking for in task 1. So basically, yeah, we run our script, we input these 3, and it's going to output the total moles fed to the reactor, moles of ammonia produced, and the overall fractional conversion of nitrogen. From there, task 2 is going to graph the relationships that we set, and basically we just analyze these relationships and determine in task 3 which independent variables we maximize and which independent variables we minimize to optimize the production of ammonia down here. So I'll run that for you. Just put in a test case here, and we see here, given 3 figures, figure 1 is going to show us that the more gas that leaves the condenser, basically, the less ammonia will be produced. So figure 1 shows that the moles of ammonia produced will decrease as the fraction of gas leaving the condenser increases, which is shown here. It's easy to see. Fraction of gas leaving the condenser up to 1, moles of ammonia produced keeps decreasing. Figure 2 is going to show us that the moles of ammonia produced will increase as the fractional conversion increases. So it's a good thing. This one shows us, so as fractional conversion in the reactor increases all the way to 1, moles of ammonia produced keeps increasing. So that's a good sign. And figure 3 shows that the moles of ammonia produced will decrease as the amount of inert gas moles fed increases. So here we see it's another decrease in moles of ammonia produced. This one is for mole fraction of inert gas in the fresh feed, which makes sense. And so basically from there, we task 3, optimize the system. From those graphs, what do we want to maximize and what do we want to minimize? We saw that there was only 1 increase in the production of ammonia. So obviously we're going to want to maximize the second this is our only increase in moles of ammonia produced. So we're going to want to increase the fractional conversion of the reactor and decrease these 2, fraction of gas leaving the condenser, mole fraction of inert gas in the fresh feed, And so basically we just summarize that here in the command window. Based on the graphical observations, it can deduce that in order to optimize the production of ammonia, you must minimize inert gas, as well as fraction of gas leaving the condenser, and maximize the fractional conversion of the reactor. And so we just go on to explain that, the whole relationship and how it makes sense. And task 3 also asks us, let's see here, calculate the theoretical maximum production of ammonia. So we do that here as well, which is given by this. Theoretical maximum production of ammonia is 0.4, so that's a fraction. And then we move on to task 4 right here. So task 4's got its own function, cooling function, and it asks us basically create a function that, using the same 3 variables, basically find cost to cool the gases and condense the ammonia, and basically allow the user to keep inputting different values until they no longer wish to repeat. So we'll run that here. So this is a cooling function. It's very similar to the chemical converter function, except for our output here is the cost. And basically, we start off, we just convert all our units, find the temperature difference, kilomoles to moles per hour, kilojoules to joules, all that stuff, all the conversions. And basically, we're going to run task 4, and it's going to ask us, so we can just put in whatever within the parameters, of course. And it tells us here, total cost to cool the gases leaving the reactor and condense the ammonia is $2,472.18 per hour. And so, of course, it says until the user wants to stop. So if we want to keep going, hey, yes. Just another random set of numbers. Cost is here. And say yes again. And say we obviously mess up the parameters, we can show that the program will be terminated because this one up here, desired mole fraction, has to be below 0.99. So with an input of 1, it's going to terminate the program. And finally, I'll just show you that we also can terminate it just by typing nope, and program successfully terminated. So that's our group code for project 2 for the chemical process problem. And so this code is pretty useful in obviously this problem, this ammonia production problem, but it also has other applications, any other chemical process, not any other, but many other chemical processes problems, production problems, optimization problems could be solved or analyzed using code like this. But this code obviously has its limitations as well, and it only intakes, well, user can only input these 3 variables, as well as only get the output, these 3 outputs. So it's got limitations, but it's also got other applications, such as other optimization problems, minimization, maximization, other things that come into question. And so that's our group code, and I hope you liked it, and thank you for watching the video.